Alright, so today we're going to look at simplifying radicals with kind of two techniques, a prime factorization technique and then also factoring perfect squares. Factoring perfect squares is kind of important because it's useful in many things, but so is prime factorization. So let's first kind of look at prime factorization. So from early on in early grades, you'll remember you are factoring it, and since we know that we're looking for the square root, since there's no number there, I'm just going to factor what numbers go into this value. And so let's kind of look at, I know I have 16 times the square root of 5. Okay, and now let's factor, this is prime, so I can factor it again to we'll say 8 times 2, and I'm keeping the square root symbols over it because it reminds me that I'm still talking about a radical, so we're still simplifying a radical. So I'm going to get all my prime numbers, and then I'm going to have the square root of 4 times the square root of 2, right? 2 times 4 is 8, 2 times 8 is 16, 5 times 16 is 20. And we're going to factor this one more time to the square root of 2 times the square root of 2. So if I take this example, I have 1, 2, 3, 4 2's. These are the prime factors of the value of the square root of 80, right? So if I was to take the square root of 2 and just put all these numbers right here, times this 2 times 5, all of these multiplied equal 80, and see these are all prime, and that's what they mean by prime factorization. These are the prime factors of 80. So for every, and this is kind of complicated, but for every 2 square roots, right? I'm just going to kind of show you that the square root of these two numbers is just one of those. So I can kind of simplify this to this first group right here being 2. I can simplify this next group to it being 2, and then times the square root of 5. And so prime factorization tells us that this is 4 square roots of 5. I will kind of go through some logic behind why this works, but let's just factor all of them. Actually, let's go through the logic and then we'll factor the other two, and then we'll look at this other side, which will really accelerate the capacity for this. So let's take a look at, alright, so when we're talking about 2 times 2, we get the area. Let's say if I do this and this, I get 2 times 2, that's the area of a square, right? Gives me an area of 4 if one side is 2. So when I'm asking for the square's root, right, so if I take this 4 and I want the square root, I'm asking for just one side of the square, which is 2. So the square root of 2, or square root of 4 would be 2, simply because it's asking you for one side of the square, which is the root. When we get into irrational numbers, that's a little more complicated. But let's look at this situation over here. I can factor this to 25 times 3, and again, I am a square root, so I will put that over, and then this is 5 times 5. So here are my prime factors of the square root of 75. Again, I would have the square root of 5 times 5 times 3. Those are all prime factors that multiply up to that. But if I kind of separate it, where I have this situation where I have 2 5's times the square root of 3, and obviously the idea of these 2 5's, the square root of both of them just gives me one side, because the square root of 5 times 5 is really the square root of 25, and that's a perfect square, right? Okay, so let's try this one right here with the same idea. Let's see, I could say the square root of 3 times the square root of 9. Now 3 doesn't have a factor, just like it's prime, just like 5 2 2 2 2 and 3 5 5, they are prime, and then I can factor this to the square root of 3 times the square root of 3. I'm going to pull this problem right over here just so we can kind of see that these are my 3 factors. 3 times 3 times 3 is 27. So I'm going to say 3 times 3 times 3. Of course, they're all underneath the root symbol, but I'm going to break it up. So for every 2 underneath the square root symbol, it leaves me with 1 outside, right? Because the square root of that 9 is this 3. And so this would be my answer to that question. So 3 square roots of 3 is the answer to simplifying the square root of 27, just like 5 square root of 3 is the simplest form of this square root of 75. Well, if we want to kind of go faster, and prime factorization is useful for understanding, but we can go faster if we know these numbers, these perfect squares, because I can factor out the largest perfect square. So what do? I'm going to go to half of 80, and in this list it's 40, but 36 doesn't go in, 25 doesn't go in, 16 does go in. 16 goes in 16 times 5. And look at this. I already know that the square root of 16 is just one of these two numbers. So that's 4 times the square root of 5. So if you know your perfect squares, you can save a bit of time. And then over here, we have the square root of 25 times the square root of 3. And again, go here. 5 is that one, and 3 is just a prime number. And over here, we can kind of think of it again. We can say the perfect square, and then in the square root of 9 is 3. So we have our answer. And anytime I'm looking at factoring, right, I have this base that my first factor over here is my perfect square, and then over here is what's left over. Okay, left over. It just helps with kind of keeping organized if you keep things in position. But notice I did not remove my square root symbols. A lot of my students do, which isn't going to be bad in terms of the outcome if you know what you're doing. It's just not presentation-wise clear. So that is factoring perfect squares and prime factorization of basic radicals. So